The talk's topic is reduced predictive model for microtearing mode in the pedestal. Understanding microtearing mode is important. The pedestal is a key to the confinement of the tokamak. It's important for us to understand the transport mechanism in the pedestal of all channels. MTM is one of them. We can observe the microtearing mode in the magnetic spectrogram, and we found that MTM is a main contributor of electron heat flux in the pedestal region. The following publications support such idea from the perspective of simulation, theory, and experiment. One of the example is the D3D discharge shows two magnetic fluctuations, one at the toroidal mode number n equals 3, another at n equals 5. Both toroidal mode number can be found using only the experimental data using the code MOSPEC. The gyrokinetics simulation can find those unstable microtearing mode that give us quantitative agreement with those frequency band. And in this talk, we will provide a fundamental understanding using the global MTM theory. And we'll use the newly developed theory to apply for a set of discharges to reproduce the spectrogram. Let's familiarize ourselves with the definition of pedestal and electron diamagnetic frequency. The top plot shows the profile of the pressure. The green highlighted area is considered pedestal, where the pressure have a sharp drop, and the peak of the pressure gradient is considered the mid pedestal. Based on the definition of electron diamagnetic frequency, it's not hard to see that the peak of omega star E will be located at the mid pedestal. The bottom plot shows the omega star E profile. It is well known that stability of a slab like MTM is dependent on the variety of parameters such as KY, eta, S hat, beta, and nu. The newly developed global MTM theory by Joe Lariker found that the two new parameters that is important for the stability of MTM, mu and X star. Mu can be defined as the distance from the rational surface marked as a red vertical line to the peak of omega star E marked as a red vertical line. And X star is square root of sigma, where sigma is the standard deviation of a Gaussian function. Where the omega star E will be fitted with a Gaussian function. In other words, the X star can be considered as a spread of omega star E. The mu over X star then will be a really good parameter to describe the alignment of the rational surface to the peak of omega star E. The bigger the mu over X star is, the further the rational surface is away from the peak of omega star E. We studied the dependence of such new parameter. We found that the MTM fastly becomes stable after the rational surface stay away from the peak. As you can see, the mu over X star drop almost to 0 at mu over at 0.3. Just to make it more intuitive, the mu over X star is less than 0.3 is about top 8% of omega star E marked as a purple shaded area, as you can see here on the right hand side plot. With the idea of the top few alignment of rational surface will give us unstable microtearing mode. If it's further away, will become stable. We can have a faster way of determining whether the microtearing mode is stable or not. Let's demonstrate such model. We call it SLiM fast. SLiM is a short of a slab-like microtearing mode. The green curve is omega star E from toroidal mode number n equals 1 to 2, 3, 4, so on and so forth. We have two vertical line marked for the radial stability boundary that calculated using the global global slab MTM model. And we have two horizontal lines that either can be confined using the analytical model or from the frequency observed from the experiment. Those four lines give us a highlighted area considered as an unstable area. If I have a rational surface intersect with omega star E within the unstable area, like so, then this rational surface is likely to host unstable microtearing mode. On the other hand, if the rational surface intersects with omega star E outside of the box, then this rational surface does not have unstable microtearing mode. Here is a model that we are going to compare between each other. From the top to bottom is from complex to simple. The top is a global linear gyrokinetic simulation for using gene. The output will be the moment of the species. It will take roughly 10,000 core hours to finish. The SLiM, slab-like microtearing mode, have two modes. One is slow, another is fast. Slow is basically calculating dispersion relations and developed by Joe Lariker. And we get the growth rate and frequency will give the result in terms of minutes. The fast will basically see the alignment of rational surface to the peak. It will give us whether that mode was stable or not within seconds. So now we're familiar with the SLiM model. We are going to apply such model to 4 discharges in order to explore the usage. We'll use the model to predict unstable microtearing mode, determine the poloidal mode number, and constrain the safety factor at the pedestal region. Let's study the first discharge, a D3D discharge. It has 3 frequency bands. A lower frequency, we have 2 bands marked with a red circle. One at 45 kilohertz, another at 85 kilohertz. And the broadband at a higher frequency ranging from 300 kilohertz to 500 kilohertz. Remind ourselves we're studying slab-like microtearing mode, therefore we're constrained ourselves within relatively low frequency, say less than 200 kilohertz. The gyrokinetic simulation predict that n equals 3, 5, and 6 are unstable, while 4 being stable. It gives us a discrete frequency band that is resemble to the experimental observation in the middle plot. Let's use the alignment of rational surface to the peak to study the stability of MTM for that case. For n equals 1, we have a rational surface on the right with orange vertical line is falling outside of the unstable area, so there's no unstable microtearing mode. Same for n equals 2. For n equals 3, the rational surface on the left intersects with omega star E inside of the box, therefore this rational surface on the left holds an unstable microtearing mode. Similar idea, n equals 4 stable, 5 unstable, 6 unstable. In summary, on the right hand side plot, we see that n equals 3, 5, and 6 are unstable predicted by the alignment of the rational surface to the peak of omega star E. And we'll also calculate dispersion relations using the reduced model marked as a red dots to compare with the gyrokinetic simulation using gene marked as blue dots. Both predicted that n equals 3, 5, and 6 are unstable, while 4 being stable. So one more discharge in jet give us an idea of the nonlinear effect. Global linear simulation predicted n equals 4 and 8 being unstable, marked as a red dashed line. The global nonlinear simulation broadened the frequency band and shipped down the frequencies that is resemble to the experimental observation. One band at 68 kilohertz, another at 130 kilohertz. If we plot out the rational surfaces, we found that n equals 4, 8, and 12 are aligned almost perfectly to the peak of omega star E, while the other are rather further away. The dispersion relations calculated by SLiM, the red dot, and the gene simulation, the blue dot, predicted n equals 4, 8, and 12 are unstable. It's worth noting that the frequency predicted by Bose model are pretty much the same as the omega star E for the given rational surface location. We can use that idea to predict the poloidal mode number. Here is an example in the D3D discharge. On the left-hand side, that's the rational surfaces with different poloidal mode numbers. You can get the frequency at that given time slice. And you can plot out all the frequency for each time slice with different poloidal mode number, as you can see in the middle plot, ranging from 15, 16, 17, 18. And you overlay with experimental observation, the spectrogram, then you find that the poloidal mode number M equals 16, matching the best with experimental observation. Therefore, it's likely that this frequency band has a poloidal mode number of 16. For low magnetic shear case, we found that the placement of the rational surface is highly sensitive to the safety factor. For example, on the right, the nominal Q profile is a red curve, has a rational surface that is further away from the peak of omega star E. If we shift down the shift down the safety factor by 2%, then we found that the rational surface will align perfectly with omega star E. This 2% of change give the rational surface from stable to unstable. Therefore, it's very useful for us to use this to exploit that idea to constrain the Q profile in the pedestal region. A sneak peek for the future, we would like to use such idea to further constrain for equilibrium reconstruction. We can calculate the frequencies to see if it matches with the experiment, and then we try to refit it into the equilibrium reconstruction until we get the equilibrium that is desired. But however, for this talk, we are going to only vary the Q profile while keeping the other the same. So let's use that method, the changing the Q profile method, to study one more discharge. At the very beginning of the talk, we have talked about the toroidal mode number 3 and 5 are unstable in this discharge at time equals 3560. It's worth noting on the left-hand side plot, you see the omega star E in the left frame. The peak has about 22 kilohertz. That means that's for n equals 1. Then n equals 3 has a peak at the 66 kilohertz. N equals 5, 110 kilohertz. Right off the bat, those two frequency band is suspect to be a microtearing mode. We have orange vertical line on the left-hand side considered as a stable range. Then we can plot the rational surfaces as a horizontal line with the width of the radial stability boundary, with n equals 3, 4, and 5 having have a color orange, green, and blue. Red, green, and red. Recall that n equals 4 is stable. Therefore, our objective is modify the Q profile so that the modified Q profile will go through the orange and red while avoiding the green. The nominal Q profile, the blue one, doesn't do that. Downshift by 2% will give us the desired profile, while the shifted profile will go through n equals 3, the orange, and n equals 5, the red. So let's use the profile downshifted by 2% and do the simulation. We found that n equals 3, 5, and 6 are unstable, marked as a red dot on the left-hand side. And the red horizontal line are the frequency that for n equals 3, 5, and 6. As you can see, it matched quite nicely with the experiment. But it's quite obvious that n equals 6 doesn't have the experimentally observed fluctuations. So we can actually modify the Q profile in a different way. We don't upshift it by 3%. Then the Q profile will go through 5 in the center will barely go through n equals 3. Therefore, since n equals 6 is starting to become stabilizing, therefore the 6 will become stable if we get the profile upshift by 3%, as you can see the orange curve. We use the upshifted 3% profile, did a set of global linear simulation, finding exactly what we're expecting. N equals 3 and 5 are unstable, while 6 and 4 are unstable. And the red horizontal line are the frequency predicted by the gyrokinetic simulation. So I would like to emphasize that this is a very powerful message. You can shift the Q profile with certainty on what fluctuation, what toroidal mode number, what to be unstable by using the plot on the top. Just shift it so that it goes through the certain rational surfaces while avoiding the one that is not desired. If you go through the center, it's becomes strongly destabilizing and is barely at the edge, then it's barely unstable. On the left-hand side, the we did a global linear simulation with a varying Q profile from -5% to +5%, and the right-hand side is the local linear simulation for the same scan. As you can see, the global linear simulation have a changing the stability of MTM from stable to unstable by changing of 1%, marked as the red dots. While the local linear simulation doesn't seem to be bothered by such change. It should come obvious by now, at this point of the talk, the stability of MTM is dependent on the alignment of rational surface to the peak of omega star E. Such effect is a global effect. Therefore, the local linear simulation will fail to capture such effect. Let's put it more visually. On the left-hand side is the Q profile change downshift by 2%, and the right-hand side is a nominal profile. The red vertical line is an unstable rational surface. The green is the stable rational surfaces. The blue curve is omega star E. The orange curve is a Q profile. As you can see, the one that has unstable microtearing mode is aligned nicely with the peak, while the stable ones are not. The bottom is the amplitude of A parallel. The y-axis is a ballooning angle. The x-axis is a rotor. And the brighter it is, the higher the A parallel amplitude. As you can see, the one that has a rational surface with unstable microtearing mode has a high concentration of amplitude of A parallel, while the others doesn't seem to have it, and that's a feature that MTM has. If we extract the distance from rational surface to the peak, from the gyrokinetic simulation marked as the blue dot overlay with the SLiM dispersion relations calculation at beginning of as we has discussed at the very beginning of the talk, we find both the simulation and the reduced model predicted that it's highly stabilizing as the rational surface goes further away from the peak of omega star E. Right around 0.3, it becomes completely stable. Just to remind ourselves, at mu over x star, less than 0.3 is about top 8% of omega star E, which is marked as a purple shaded area. In summary, as a concept of alignment rational surface to the peak, give us the ability to have a near quantitative reproduction of the distinctive frequency band in several discharge in D3D and jet, and have more case study ongoing. So SLiM give us the chance to identify the poloidal mode number of the magnetic fluctuations. It can also be used to constrain the Q profile in order to have a higher accuracy equilibrium reconstruction. In the future, we would like to study more experimental discharges. We would like to understand and quantify the nonlinear frequency reduction, and we will exploit the SLiM model to constrain the equilibrium-free reconstruction. And the top is the link to the record of the link of this talk. You can scan the QR code on the right. And the bottom is a GitHub repository for the SLiM model. Here's a link, and the left is a QR code for the link. And here's the reference, and thank you for your attention.